Good afternoon, everybody. My name is Ethan Klein. I'm a third-year PhD candidate in the group of Professor Ari Danagulian at MIT. And today I'll be talking to you about using a DT portable neutron generator to perform neutron resonance transmission analysis for nuclear security applications. To motivate our work, our primary objective is to perform on-site material identification and isotopic composition analysis with the goal of supporting verification of arms control and nuclear safeguards treaties. The main challenge that we face is that X-ray imaging and many passive detection techniques simply don't have sufficient penetration within mid and high Z materials in order to perform isotopic identification, especially if those materials are shielded or in high radiation environments. So what we are proposing is the use of epithermal neutron resonances to perform isotopic detection and quantification in a portable package using portable neutron generators. The relevance to the Nnsa mission is that epithermal neutron resonance imaging has already been demonstrated for imaging both fresh and spent nuclear fuel for safeguards applications, and in the past has been proposed for the idea of having stronger compact neutron sources to be able to extend that technique to an on-site application. And so if we are successful in actually moving this to a mobile capability, it could expand the utility of NRTA to on-site nuclear inspection, both for arms control treaties as well as nuclear safeguards. In addition, our group has done prior work on warhead verification measurements, which represent a novel use case for NRTA to identify potential non-compliance with international treaties. And just on this slide, I just show a few graphics for you. In the upper right is work done by Chichester and Sturbence about a decade ago, just demonstrating the ability for NRTA to characterize spent nuclear fuel. And in the bottom right, you see a figure from previous work from our research group, again on physical cryptographic warhead verification techniques. So to jump into some of the physics behind this neutron resonance transmission analysis. So where do neutron resonances come from? Just looking at the left-hand side of the screen here, you see that if we have an incident neutron N, incident on an atomic nucleus of mass A, it has a likelihood of forming a compound nucleus, and if the energy of that incident neutron matches one of the energy levels of that compound nucleus, we expect to see an increased likelihood of interaction, increased cross-section for that neutron energy, which we term a nuclear resonance. The result of that, as you can see on the plot on the right, is that for many fissile and other isotopes of interest to nuclear security, uranium and plutonium isotopes, for example, have these neutron resonances in the epithermal neutron region. And furthermore, these resonances are isotopically unique. So, for example, we can distinguish the spectrum for U-235 from U-238. And furthermore, for many common shielding materials, such as organics and different kinds of metals, we find that they have no resonances in the epithermal regime. So this indicates that while they may attenuate our signal, they won't contribute anything to complicating performing isotopic identification using analysis of those neutron resonances. So the question then becomes, how can we actually use those resonances to identify and quantify isotopic composition? And furthermore, how can we do it in a manner such that we could actually support portable on-site applications? So the answer, as I mentioned before, is to use neutron resonance transmission analysis, or NRTA. Just a simplified diagram on the left here that I'd like to walk through. So we start out with a neutron source. For us, it's a portable DT neutron generator. So we create neutrons at around 14 MeV, and we slow them down in a moderator down to epithermal neutron energies. Of course, we lose many neutrons in that process, but we still have sufficient neutron flux to perform measurements in the time of 10 minutes to an hour runtimes. Those neutrons will be incident upon a target, and depending on the isotopic composition of the target, will determine how many neutrons and of which energies are actually transmitted through the target. And then we measure those neutrons in a detector, lithium-6 glass scintillator, which is very efficient at capturing epithermal neutrons while not capturing any of those fast neutrons that may have been coming in from our DT neutron source. And so in the top right, you'll see just a plot of synthetic data. And the black line there represents our open beam, so essentially just the epithermal neutron flux coming from the moderator incident on our detector. In red, you'll see an example spectrum for maybe shielding material, something like a target just that is solely composed of lead. It will, again, attenuate our overall signal, but it won't contribute any energy-dependent features. And if we have resonant target present, that includes mid and high Z isotopes and elements such as silver, indium, tungsten, and of course uranium and plutonium, we expect to see attenuation dips at the characteristic resonance energies of the isotopes contained within the target. So when we take the ratio then of the target in to the target out spectrum, we can use this formula that you see in the bottom right here and calculate just an exponential attenuation of the neutron signal. And so that's the plot that I'm showing in the bottom right there. And so by using that formula along with the actual experimental data that we have, we can then use that to infer the composition of the unknown material within the target. And one thing I should note is that although our signal is in the time domain, we have to convert that to a neutron energy. We do that using a time of flight reconstruction. And so that's performed just by taking the distance between the moderator and the detector with a few corrections for moderation time and any off-axis effects. And then we can just use essentially 1/2 mv squared, where velocity is that time of flight distance divided by the difference in time between our start of our neutron pulse and the time of detection. So our technical work plan for this was to perform MC&P simulations of the actual neutron moderation process in our moderator from our DT source to characterize our pulse height response in the lithium-6 scintillator, as well as to better understand any radiative capture gamma background. So any gammas that are being created through neutron capture in the surrounding environment. Then we performed NRTA experiments of targets, either single elements or multi-element targets, objects at our lab at MIT, where we have a DT neutron generator. And thirdly, we actually then performed our isotopic composition analysis using refit 2009 code, which is essentially just a least squares fit using a whole bunch of different resolution parameters for the data. And we're currently in the midst of several collaborations with national labs that we hope will lead to experiments using special nuclear material to be able to further test this capability for uranium enrichment analysis, for example. So what does our experimental setup look like? So on the left-hand side, you'll see a DT tube. And here I just indicate with that green dot where the DT neutrons are produced nearly isotropically. We put a radial moderator of plastic just surrounding that to moderate those neutrons down, and then borated poly shielding just to minimize any thermal neutrons from scattering around the room. So that's a pretty efficient at capturing those room background. The neutrons then will be incident from the moderator down towards, on the right there, our target and detector assembly. So you see the target with cadmium foil. Cadmium essentially removes wraparound neutrons, so neutrons from a single pulse that may be so slow that they would be detected in a subsequent pulse. And then we have both boron carbide shielding to remove neutron background, as well as lead shielding to remove gamma background. And as I mentioned before, our detector consists of lithium-6 glass. We have these three 1-inch diameter pieces of glass just adjacent to each other, and that's coupled to a PMT and then to our digitizer. So here's what that setup actually looks like in practice. Again, just on the left-hand side, you see the source moderator assembly. On the right is our shielded detector setup. As I mentioned, we're using a DT neutron generator with a nominal 1e to the 8 neutrons per second, emitted isotropically. Again, the nominal pulse width is 10 microseconds, but in actuality, it's really closer to 3.3 microseconds, which is sufficient for reasonable energy resolution at epithermal neutron energies. As I mentioned, our moderator is just 4 inches of plastic, and our time of flight distance is much more compact than some of those larger experimental facilities. We only have a distance of maybe 2.5 meters compared to maybe those 35, 50 meter beamlines that you may have seen in the past. And again, our detector is that enriched lithium-6 glass GS20. So what do we do then with the signal that we get? So here I show you the open beam and then an example signal of the counts per minute using tungsten and silver targets. On the right-hand side, you can just see our target with cadmium foil layered behind. We have neutrons incident upon it, which then move on towards the detector. What we want to do really is to be able to fit our background. So we looked to literature, found a reasonable background fitting function that captures a constant background, something from neutrons that are being thermalized in the moderator, being captured, and then emitting these characteristic 2.2 MeV gammas, as well as an additional term for any in-scatter of neutron background in the room. We can fit that function to the bottom of these saturated peaks. So tungsten has very strong neutron resonances, such that at the bottom of those peaks, we don't expect to see any counts. So we can attribute any remaining counts in those bins to background. We perform that fit, and then we can subtract that background from the total number of counts that we see for our experimental runs, and then accounting for the target thickness, which will further attenuate that gamma background. So we can perform those corrections and then calculate a transmission, again, which we use to infer isotopic composition. So here's some initial results for single element targets. So on the right here, I'm showing indium, tungsten, silver, and uranium, all in the range of sub-millimeter up to a couple millimeters. And you'll see that those identification times are pretty good. And that's because we see these really strong resonances at the characteristic neutron resonance energies for each of these different isotopes. So all of these plots were for 2-hour runs. And then we just compare the experimental data to calculated data, which is this black line that fits very nicely to the experimental data. And just in the bottom left there, I'm just noting that it's, again, that calculated transmission function I showed before, convolved with our Gaussian neutron pulse width, which provides, again, the majority of the uncertainty in our resolution. And so I'll just note again that you can see identification time is very good for these very thin targets. And so that's something that we're still trying to hone in on, is to really understand better how quickly we can identify presence of individual isotopes. Next, I'll show a plot for 5 millimeters of depleted uranium target. And so here we use the refit code to actually give us a fit isotopic composition, assuming that there's presence of uranium in the sample. We see that that matches very nicely to the actual abundance for this depleted uranium sample. And we see that we're really nicely able to see resonances up to, again, just below 40 eV for uranium-238. And so this data now is for a 2 millimeter depleted uranium target, so much thinner, in addition to a full inch of lead. So an example of a shielded target here. Again, we perform a fit using refit code, assuming just presence of lead and uranium. Our initial fit assumes that it's entirely lead, and you'll see that the code itself can pretty easily infer that there's several millimeters of uranium, which matches very nicely to the true thickness of depleted uranium in this target. And so that fit can be performed on the order of several minutes. And so we see here, even when uranium is below 10% of the total composition, we still have very easily identified. And these were both 2-hour runs, I should note. So in conclusion, epithermal neutron resonance spectroscopy is isotopically sensitive. We believe it has potential for nuclear security applications. We've been able to demonstrate feasibility and have reasonable agreement with using MCMP simulations. And essentially our current ability to detect uranium-238 and depleted uranium targets is on the order of minutes and on the order of an hour for shielded targets. And really our next work really wants to focus on actually automating the isotopic identification. So current fitting procedures generally assume that you have a good understanding of the target object under observation, because those are primarily been used for cross-section calculations. So we really want to see is, if we don't know much about that target, can we actually identify whether there's presence of uranium or plutonium, and then quantify the isotopic composition. So the impact of MTNV has been just tremendous. The workshops have been a great source of feedback, so I hope I'll get some great feedback after this talk. And that led to actually collaborations with Dr. Rob Goldston at PPVL. I also participated myself in the MTV summer tutorial on MCMP, which I found tremendously valuable, especially in this internship that I participated in at Lawrence Livermore last summer, which I've continued on until now. And we've also begun a new collaboration with Pacific Northwest National Lab for arms control verification applications of this technique. So with that, I'd just like to thank all of you for your attention and look forward to your questions. Thank you.